Hello. So today I wanted to learn about industrial IO. So this is a subsystem within the Linux kernel, which basically is used to control or interface the various sensors like accelerometer and magnetometer, like that. This I haven't looked before, so I wanted to understand this and get little information or development aspects, what it is and how it works. So our our goal is basically to understand what is this IIO subsystem. So we'll just note down what will be the various items that I would like to learn, and maybe via the documentation provided by Linux kernel and by looking at the drivers as well. So first of all, what is IIO subsystem? Okay. Now when we say there are sensors, right? So sensor will be based on some interface mechanism, either I2C or SPI. So how does IIO interface with this hardware communication layer, right? Now similar to the lower level going to the hardware side, this IIO would also be interfacing with user space, right? Of how the data gets passed to the user space from the IIO subsystem. That we will also try to understand. Okay. It will be more of documentation read as well as looking at the drivers provided already in the Linux kernel. So we will take some drivers from the code base, and we'll go through that and try to understand and correlate with the documentation provided by the Linux kernel. Okay, so let's start with the introduction. The main purpose of the industrial IO subsystem IIO is provided to support devices that in some sense perform either analog to digital or digital to analog conversion, or both. The aim is to fill the gap between the somewhat similar hardware mono input subsystem. I'm not sure how hardware mono input internally works, but yeah, they say it's similar to that, or these kind of analog to digital and digital to analog peripherals. So basically sensors, right? When you have for example accelerometer that senses the direction of the movement of the sensor and translates to a signal, and in terms of coordinates of x and y, and sends it to the system. Similarly, magnetometer is also there, which is used to detect the magnetic field around the sensor. So that is also analog to digital conversion. So this basically for those sensors kind of devices, as I said earlier. Hardware mon is directed at low sample rate. Okay, sensors used to monitor and control the system itself. That means there is to be low speed of data rate. Okay, like the fan speed control and temperature measurement. Input is, as its name suggests, focused on human actions, input devices like touch screen, keyboard, mouse. In some cases, there are considerable overlap between these two, like hardware monitor and IIO, and input and IIO. Okay, so they have listed some devices basically, as I said, accelerometer, ADC analog to digital converter, CDCs, DAC, DACs, gyroscopes also is there. Okay, color and light sensors. So basically infrared, right? There is a IMU. So this is generally a mix of two or more sensors, like gyroscope and accelerometer. So they call it as a IMU. It's a pressure sensor, proximity sensor, and temperature sensor, and so on. Okay, as I said, yeah, right. Usually these sensors are connected via SPI or I2C. A common use case of this sensor device is to have combined functionality, that is light plus proximity sensor. So as they said, right, there will be a interface mechanism between the target, your processor where this Linux kernel is running, and the sensor, either SPI or I2C. So there will be a mechanism to make connection, like interpret the data or transfer the data over these protocols. And let's go to the core elements. Okay, Industrial IO Core offers both unified framework for writing drivers for many different types of embedded sensors and standard interface to user space application manipulating the sensors. The implementation can be found under drivers IIO, Industrial IIO. Okay, let's go to the kernel code base, maybe Linux Kernel Elixir. We'll use the online code base with the latest. What they call it, drivers IIO Industrial. Okay, so this is the code base of latest kernel 6.15.3. We'll go to drivers and go to IIO and the okay. So this is basically, I believe, as they say, Industrial IIO core, as they mentioned. All the files within this are called core files, and I think these are the categories of the various sensors which is supported by IIO. There is an accelerometer, ATC, there is some chemical sensor, there is a frequency, gyroscope, magnetometer, orientation sensors, potentiometer, pressure, proximity. Okay, cool. Okay. So basically these files in the parent directory of IIO implements the core logic of IIO subsystem. These things within these directories should be specific to a sensor implementation. That's my guess. Okay, IIO device struct. Okay, there is a main struct called IIO dev. Okay, an IIO device allocates this particular IIO dev structure within the driver. Same can be freed. IIO device free, IIO device register a device with IIO subsystem, and unregister. Okay, so this is the main data structure which represents an IIO device. You need to allocate a device using this API. This can be freed using the correlated API. There is also IIO device register. Basically you are allocating one device and then you are registering with the subsystem. These two main steps. Okay, an IIO device usually corresponds to a single hardware sensor, and it provides all the information needed by a driver handling device. Let's first have a look at the functionality embedded in an IIO device, then we will show how device driver makes use of IIO device. Perfect. That's also we are looking for. There are two ways for a user space application to interact with the IIO driver. There is a sysfs, which is populated as a sysbus IIO devices. IIO device x means represents some number. So this represents a hardware sensor and groups together the data channels of the same chip. Okay, data channels. Okay, we will know maybe soon. Dev IIO. Okay, this is a sysfs entry and this is a dev entry. Okay, the same way, same name will be there, I believe. The character dev node interface used for buffer data transfer for events information retrieval. Didn't get much. A typical IIO driver will register itself as an I2C or SPI driver and will create two routines, probe and remove. Okay, so basically I know about I2C. So I2C is like it's a communication protocol, right? So there is by a processor we have a bus node in the device tree which represents a I2C bus, and its corresponding driver is called I2C bus driver, and for each I2C device connected to that particular I2C bus we will have a corresponding client driver. So basically for each client driver we will have implementation of probe and remove for which get invoked by the driver on each device. And so whenever there is a new I2C device of that type gets detected, the probe function will be called, and the same way it will get remove will be called when the device is removed or intentionally, or maybe okay. At probe, okay, so basically what they say is that we will register the driver, IO driver, as a I2C or SPI based on the type of interface supported by the sensor. Within that probe function, we will call IIO device, which allocates the memory to IIO device. We saw this here, right? And initializes IIO device field with driver specific configuration, okay, names and channels and stuff, okay, and call it IIO device register. This registers the device with the IIO core. After this call, the device is ready to accept the request from the user space applications. Okay, so basically what they say is that we'll do allocation of IIO device within the probe function of a given I2C or SPI driver, and after filling our sensor specific fields or data specific for IIO device, maybe we'll get to know soon, and then we register the particular driver device with the IIO subsystem, so that user space can now access the device and consider it as a ready. Okay, at remove, we free resources allocated in probe in reverse order. So basically, earlier you did IO device allocation and then register. Here you will do unregister first and then free the allocated device. Okay, as same as every other device driver in the Linux kernel. Okay, next is IIO device sysfs interface. Attributes are sysfs files used to expose chip info and also allowing application to set various configuration parameters. For device with index X, attributes can be found under this plus IIO devices, device IIO colon device X, okay, directory. This will be a directory, and common attributes are name, okay, name of the physical chip. Dev shows the major minor pair associated with the corresponding care dev node. Sampling frequency available discrete set of sampling frequency values for device. Didn't get quite much, but okay, we'll go with some assumptions. Available standard attributes for IIO device are described here. Okay, file documentation testing sysfs plus IIO file in the Linux kernel source. Okay, maybe we can check this sometime. We'll keep it open. We need to open in the code base. Okay, IIO device channels. Okay, we saw this thing here, right? Somewhere. These channels. Yes, device channels here. Okay, they are explaining it now. Okay, IIO device channel specification of a single channel. Struct IIO channel spec. Okay, an IIO device channel is a representation of a data channel. An IIO device can have one or multiple channels. For example, a thermometer sensor has one channel representation representing the temperature measurement. A light sensor with two channels indicating the measurement in the visible and infrared spectrum. An acceleration can have up to 3 channels representing acceleration X, Y and Z axis. Okay, so whatever data points a sensor is capturing, those many channels will be there. An IIO channel is described by a struct IIO channel spec. A thermometer driver or temperature sensor in the example above would have to describe the channel is as follows. Okay, so there is we are defining a IIO spec structure, naming it as want temperature channel, and okay, there are setting some fields called type, which is IIO temperature, maybe some enums. Okay, this will be like type of data, I believe, based on various data types of sensing or reported by IIO. So this is one of them, IIO temperature. Info mask separate. Okay, so with IIO channel info processed. Not sure where and how it will be used, but what this would be is something that channel info will be given as a processor data. That's what name says. Not sure, but yeah. Channel CSFS attribute exposed to user space are specified in form of bit masks. Depending on their shared info, attributes can be set in one of the following masks. Okay. Info mask separate attributes will be specific to this channel only. Okay, separate means specific to this channel. Info mask shared by type, that means attributes are shared by all channel of the same type, as you said type, right? So if there is, for example, two different channels having the same type of IIO temp, then whatever is set here by as a info mask by type will be visible in both the channels. Info mask shared by dir, attributes are shared by all channel of the same direction. Okay, this is for direction. Okay, input or output, maybe it would be like that. Info mask shared by all. Okay, all channels, same data available in all channels. When there are multiple data channels per channel type, we have two ways to distinguish between them. Set .modified field of IIO channel spec to 1. Modifiers are specified using channel 2 field of the same IIO spec structure and used to indicate a physically unique characteristic of the channel, such as its direction or a spectral response. For example, a light sensor can have two channels, one for infrared light and one for infrared and visible light. Again, let's get data channels set.indexed field of IIO's spec to 1. In this case, the channel is simply another instance with an index specified by .channel. Okay, here is how we can make use of channels modifiers. Okay, let's try to in the light channel. First type is IIO intensity modified 1. Okay, first option. Channel 2 is IIO mod light IR. Okay, it's a separate channel and it's shared. Mask is shared. Shared was not there. Okay, type IIO intensity also modified 1. Channel 2 IIO light both. Info mask separate. Info raw data. Info mask shared with IIO sampling frequency. Okay. So the sampling frequency is something which is shared between both these channels. Okay, and the data which is IIO mode light IR and IIO mode light both is separate in both these channels. Okay, and third one is IIO light. Here we have IIO channel info processed data and IIO channel info sampling frequencies as a shared. So we have sampling frequency shared between all three channels and all other are separate. These channels definition will generate two separate CSFS files for raw data retrieval. Intensity IR raw, intensity both raw. One file for process data. Okay, device X in illuminance input, and one shared CSFS file for sampling frequency. If you now understood. So here if you look at the file, so this is same IR intensity IR raw. This is the separate file. So it has a different file name, IR and both row, right? IR and both. This one, IR and both. That is for in illuminance input. So I think this is for this one, IIO channel processed. The process data is coming as a illuminance input because they have set it as a IIO light. And there is a common file. So there is no something as a prefix of the name. Simply sampling frequency which is for all three channels. Okay, next here is how we can make use of the channels indexing. Okay, IIO channel spec light channels, IIO voltage, index channel 0, channel 1, mask separate info raw, info 2, IIO voltage. This will generate two separate attributes for raw data retrieval. This bus IIO device is IIO device X in voltage 0 representing the voltage measurement on channel 0 and representing the voltage measurement on channel 1 in the voltage 1 raw file. Okay, now there is extended channel info attribute, IIO spec extend info. It has a name, IIO enum shared by shared. There is something called read and write function pointers and some private data which is unsigned PTR. Whether this attribute is shared between all the channels, shared maybe read block, read callback for this info attribute, write callback this info attribute, both can be set to null. Data private to the driver and info the attribute name. IIO enum stands for enum channel info attribute. It has a definition. Okay, the name is enum, but it's a type of struct. Nice. It has two strings, single string items, const character star, const star items, and unsigned integer number of items, set and get APIs. An array of strings. It's a double pointer. Array of string, that is means const and const. Okay, sorry, array of strings means here character star and again star. Length of the item array. Okay, set callback and get callback. Now the IIO enum struct can be used to implement enum style channel attributes. Enum style attributes are those which have a set of string which maps to an unsigned integer value. An IIO enum helper takes care of mapping between value and string as well as generating an available file which contains a list of all the available items. The set callback will be called when the attribute is updated. The last parameter is indexed to the newly activated item. The get callback will be used to query the currently active and items and supposed to return the index for it. Okay, there is again IIO enum. I think we can simply get and go through this for now because there are many. Maybe we'll get to know more by looking at the drivers rather than reading this documentation. You can definitely come back to this. Okay, there are some functions definitions also. Okay, this is the IIO channel spec structure that we have earlier defined. So it has type we are setting, right? IIO temp and IIO light and like that. There is a scan index, there is a channel and channel 2. There is an union within it. Okay, these are the mask, right, that we were setting. There is also event spec, input output differential paths. Okay, we'll not go through this for now at least. Okay, again now there is various information given. Okay, IIO dev might be useful, industrial IIO dev, because this was the main data structure. This is the main dev node basically, which gets written by IIO dev allocate. It has modes. There is a device structure of corresponding dev, IIO buffer. Okay, and const integer. There is a trigger, number of channels, name, label, info, setup ops, and private. Number of channels is also there. IIO channel spec, number of channels are there. Okay, IIO device register. IIO device register. This is a device manager basically. You don't need to free it when you do exit out or you remove the driver basically. Device put, IIO dev, IIO device get, IIO device set as a parent, IIO drive data. This is to set the private data of driver to the data structure. Debug FS entry, suspend triggering, IIO get current scan type. Okay, a lot many APIs by Subsystem. Okay. We'll go back to, okay, this we read. We'll go to buffers. Okay, so now again another data structure, struct IIO buffer, a general buffer structure. Okay, it has API to operate on. IIO validates, can mask, one shot validates what exactly one channel is selected for. Okay, not sure how it is related to IIO buffer now. IIO buffer get, grab the reference to the buffer, put, release the reference to the buffer. Okay. The industrial IIO core offers a way for continuous data capture based on the trigger source. Multiple data channels can be read at once from this dev node, thus reducing the CPU load. Okay, so trigger in general, what I understand is basically an event, sort of event, by based on which the retrieval of data or parsing of data happens. Basically, how does IIO subsystem, when does IIO subsystem reads the data, right? That's maybe related to, based on the trigger. However, whatever way you set the trigger, according to that the data will be read. So IIO buffer is a interface. An IIO buffer has an associate attribute directory under the device buffer. The IIO device structure directory, within that there is a directory called buffer, and there will be entries. Here are some of the existing attributes: length, the number of, total number of data samples, capacity that can be stored by the buffer, okay, and activate buffer capture, enable flag. Okay, IIO buffer setup. The meta information associated with the channel reading placed in a buffer is called the scan element. The important bits configuring scan elements are exposed to user space application via device X scan element directory. This directory contains attributes of the following form: enable, used to enable a channel if and only if a attributes is non-zero, then the triggered capture will be contain data samples of the channel, for this channel. Index, the scan index of the channel. Type, description of the scan element, data storage within the buffer, and hence the form in which it is read from user space. Format is okay, this is the various type of formats. For example, a driver for a 3-axis accelerometer with 12-bit resolution, where the data is stored in 2 8-bit registers as follow. Okay. Why it looks like we are always understanding something when they are giving the example. Okay, we'll have the following scan element type for each axis. Okay. Oh, okay, understood. So type is set like this. For lower bytes, you are basically LE they have given here. Specified big ND and ND. So this is total length of the data. So we have 8 bits in each byte. So we have 2 such bytes, and out of that 8 plus 8, 16 bits. We are actually need only 12 bits. This S means signed, and that is out of 16. So they are saying 16 out of 12 signed bits is the actual data. Okay, and there is also shift. Shift is specified if the shift that needs to be applied prior to masking out unused bits. Okay, so whatever data that you have, okay, now look at this low byte address and high byte address, right? So what they mean is you need to discard these values, right? So if you put it like that, like this is the first 8 bits, then these are the lower 4 bits, but it's arranged as a D11 to D0, like D11 D like this goes for D3 D2 D1 D0, and there are 4 bits only, rest are none. So you need to remove those 4 bits to get the actual 12-bit value, so you are shifting it by 4. Okay, this example helped to understand what is the scan element for. Okay, understood. User space application will interpret data samples read from the buffer as a 2-byte literal signed data that needs a 4-bit write shift before masking out the 12 bits data. Okay, this basically gives the idea to user space application who is reading this value, right? Reading value for in acceleration y axis of acceleration data, how to process the data, how the data is represented in a particular register when you read it. For implementing the buffer support, a driver should initialize the following fields in the IIO channel spec. Okay, we are looking at this. So it had there are other members, and there is scan index. Okay, the drive. Okay, so we need to specify what sign, how many bits are there, real bits. So we will have 12 storage bits. That means we are having 16 bits in total, but we are utilizing 12. Whether shift is needed or not sure what does repeat means for IIO, little endian or big endian. And that is a scan type basically. So how do you set the entire driver implementing the accelerometer described above will have the following channel definitions. The type is IIO acceleration, modified 1, channel to mode X. Okay, and scan index is 0. Scan type, okay, here they have given S, 12, 16, shift by 4 and little endian. Similar to Y, where channel 2 will become IIO mode Y, scan index will become 1. For Z, channel 2 will be IIO mode 2 and scan index will become 2 for Z axis. What does channel stands for then? If channel 2 is actually having the data, what does channel contains? Because it had a channel data field. Let's see. Here scan index defines the order in which the enabled channels are placed inside the buffer. Okay, basically, okay, so when you read the dev entry, basically there will be entire buffer that will be going out, which contains data for all 3 things, X, Y and Z. So basically the scan index is used to tell which data is first one. So here when you say scan index 0, that means the first is for X, second is scan index is 1, like that. Will be channels with the lower scan index will be placed before channel index with higher index. Correct. Each channel needs to have a unique scan index. Perfect. Setting scan index to -1 can be used to indicate the specific channel does not support buffer capture. In this case, no entries will be created for channel in scan elements directory. Okay. These are more details on the buffer. I push to buffers with timestamp. Okay, there is an API which to push the data to buffer, like whenever you read the data from the sensor X, Y and Z coordinates data, right? You want to put it within the buffer for buffer trigger with the timestamp. So it's okay. Description is already given. Push data to IIO devices buffer. If timestamps are unable for a device, function will store the supplied timestamp as last element in the sample data buffer before pushing it to device buffers. The sample data buffer needs to be large enough to hold the additional timestamp. Usually the buffer should be in the DIO scan bytes large. Return 0 on success and negative on error code. Validate scan mask one shot. Okay, return to if exactly 1 bit of the satisfaction. Okay, I push buffers with PS unaligned. A buffer get returns the pointer to the buffer that was passed into the function. put IO device attach buffer. This seems interesting. This function attaches a buffer to IO device. Exactly. The buffer stays attached to the device until the device is freed. For legacy reason, the first attached buffer will also be assigned to in the IO dev buffer. The array allocated here will be freed via the IO device detach buffers call, which is handled by the IO device. So I think this will be the first API. No, maybe some installation API will be there, right? Or this is the only. This is for pushing the data. So I believe this will be the attached buffer to IO. This will be the API to be used whenever you want to use the buffers with the IO device driver. IO buffer setup, we already read it. Okay, let's jump to triggers. They mentioned triggers in the buffers, right? Okay, so let's see if our assumption was correct. Okay, there is another data structure now called IO trigger. Industry IO trigger device, resource managed. Okay, the same version of allocation. No, DEM IO trigger allocate. This allocates resource managed IO of maybe IO data structure gets allocated. Register to be registered. Okay, trigger validate on device. Check if trigger and IO device belongs to the same device. In many situations, it is useful for a driver to be able to capture data based on some external event, as we assumed correctly, trigger, as opposed to periodically polling for data. Correct. If you keep on, like basically when you poll device to check whether the data is available or not, that is actually consuming your CPU resources. Keep on polling and checking whether the data is arrived or not. So having a trigger, we can call it as interrupt basically an event based on which you get to know, get a notification that the data is ready and you can go ahead and read it. An IIO trigger can be provided by a device driver that also has an IO device based on the hardware generated events. Is data ready or a threshold exceeded, or provided by a separate driver from independent interrupt source, CPIO line control, timer interrupt, or a user space writing specific to a sysfs entry. The trigger may initiate a data capture for a number of sensors, and also it may be completely unrelated to the sensor itself. Okay, so there can be different types of triggers. If your sensor supports an interrupt pin, you can configure the trigger to be as an interrupt pin based on CPIO. There can be, as they said, some hardware generated events, right? When the data, this will be something that I would like to understand more. How does the data ready? Maybe sensor register by reading sensor register, right? IO triggers sysfs interface. Okay. There are two locations in sysfs related to triggers. This bus IO device is triggers Y. This file indicates and created. Well, this file is created once an IO trigger is generated, registered with the IO core, and corresponds to a trigger with index Y. Because triggers can be very different depending on type. There are few standard attributes that we can describe here. Name of the trigger, maybe trigger name that can be used later for association with the device. Okay, and sampling frequency. Some timers based triggers use this attribute to specify the frequency of the trigger's calls. Okay, this is the first, and second is sysfs IO devices. These are IO device data directory. From there is a directory called trigger. This directory is created once the device supports a triggered buffer. Okay, we can associate a trigger with our device by writing a trigger's name in the current trigger files. Okay, nice. Let's see how IIO trigger is set up. Let's see a simple example. Very good. How to set up a trigger to be used in drive. This will explain maybe more details than this description could be. IIO triggers, ops, trigger ops. So set trigger state. Okay. Sample trigger state. Validate device. Sample validate device. Okay, this will be two APIs within our driver when we want to write a specific driver. And there is a data structure. First allocate a memory for our trigger. Okay, we get IIO trigger allocated. Parameters we are passing. Set up a trigger operation field, trigger ops that we set here in the trigger data structure ops, and then register that IIO trigger. Okay, by providing this dev, I think we are specifying, or sorry, with this dev we are correlating the trigger with the device, because what they mentioned here is independent. Trigger is independent to a device. There is to be a correlation made in the driver where we are tying device with a trigger. Operation structure for IIO trigger. Notice that a trigger has a set of operation attacks. Set trigger state, switch the trigger on and off on demand. Okay, validate the device function to validate the device when the current trigger gets changed. Okay, trigger ops. Set trigger re-enable and validate device. The IIO trigger has this things. Maybe this is the data structure. Associated device if relevant. Okay, dev node we are setting. Correct. So we may be passing in our IIO driver, we might be passing the dev structure which we have in the IIO dev to this. Look, let's see in the driver maybe. IIO trigger set driver data, maybe allowed to attach arbitrary pointer. Okay, it's basically a private data, right, for a driver. The trigger if you want to proceed. Get driver data, IIO trigger register, unregister, set immutable, trigger using on, tells if we use our own hardware trigger ourselves. Need to check, didn't get much. IIO trigger poll, call the IRQ trigger handler to consumers. Okay, IIO trigger poll nested. Okay, IIO trigger AVM managed. Okay, cool. We got to know about some core elements. Okay, what is the, how do we allocate a, so what is a IIO dev structure, what is, how do we allocate a device, and how do we register it. This buffer section is how the data is sent to user space basically, in a buffered manner, where all the data is clubbed into a single buffer in a specific order based on the scale element and kernel spanning index. And the trigger is based on what events we capture the data. There can be various types of triggers which you can set up. Now this seems combination of both triggered buffers. Now that we know what buffers and triggers are, let's see how they work together. Okay, now we will get to know that how this works together. Cool. IIO triggered buffer setup. Setup triggered buffer polling function. IIO triggered buffer cleanup, free resources allocated by the above one. And IIO buffer setup ops, buffer setup related. So a typical buffer setup looks like this. Okay, so we have a buffer sensor buffer setup ops. Pre-enable, pre-enable, post-enable, post-disable, pre-disable. So we have some sort of sensor buffer related callbacks which we want to provide it to set up in setup ops. IIO polling function we have defined. Sensor IIO poll function is an IRQ and a pointer. IIO get nanosecond. Okay, get a timestamp basically, and it wakes up a thread. This is an IRQ basically. It's a interrupt handler which we will be registering somewhere. And there is this This is the main IIO poll function. This is the handler. So what handler is doing is IRQ number and P for each set bit. The read data for each active channel. Okay, sensor get data, television API which getting the sensor data. IIO push to buffer, whatever data that is received from the buffer, from the sensor in this buffer, we are pushing it to a buffer. We saw this API in the buffer's explanation with the timestamp. And IIO trigger notify done. So some API and IRQ handle. Setup trigger buffer usually in a probe function. Okay, correct. So in the probe we'll be using this function where we are specifying our IIO device, the poll function, the primary ISR handler that you want to call. Then the secondary, this is the top half, this is the bottom half of IRQ. If you know how Linux kernel implements the interrupts. This gets called whenever the IRQ is coming. So this is a very short processing. Once that is done, during this the interrupt will be disabled. In general, that's what the kernel explains, that in the top half interrupts will be disabled. So this does a very little processing, and then it backs up the handler thread which you have specified here, which is nothing but this. This runs in the, it does not run in the interrupt context, whereas this runs in the interrupt context with the interrupts disabled. This runs in the kernel context, kernel process context, and this you are providing as a buffer setup. Okay. The implemented things notice are here is buffer setup ops. The buffer setup ops function to be called at predefined points in the buffer configuration sequence, before enable, after disable. If specified, the IIO core uses default. If not specified, if not specified, the IIO core uses the default IIO trigger buffer setup ops. Okay. Sensor IIO polling function, the function that will be used as a top half, as I said, it should be do as little processing as possible because it runs in interrupt context. The most common operation is recording the current timestamp. For this reason, one can use IIO core defined poll function store time. Okay, so what they are doing is simply getting a time into the PF timestamp. They are using the same timestamp here again. Okay, and sensor trigger handler, this function, the function that will be used as a bottom half, as I said, poll function. This runs in the context of a kernel thread. Sorry, I said process thread, but it is actually a kernel thread, no mistake. And all the processing takes place here. It usually reads data from device and stores it in the internal buffer together with the timestamp recorded on the top. Okay, this is then another API with some other IIO trigger buffer setup extended. This function combines common tasks which will commonly be performed when the setting up a triggered buffer. It will allocate a buffer and poll function. Before calling this, the industrial IO dev structure should be already completely initialized but not yet registered. In practice, this means that the function should be called right before IIO device register. Okay. So free resources allocated by this function, IIO trigger buffer cleanup function is also given. Okay, we got some what idea. HW consume. An IIO device can be directly connected to another device in hardware. In this case, the buffer between IIO provider and the IIO consumer are handled by the hardware. Industrial IO hardware consumer offers a way to bond this IO device without software buffer of data. Implementation can be found in device under drivers IO buffer hardware consumer.c. Select IO consumer hardware consumer structure. But basically, like if you want to connect two different IO devices, this that mechanism. A standard IIO device implementation is based on IO provider consumer, as I said. A typical IIO hardware consumer setup looks like this. Okay, so there is an ADC. They have created an IIO info for ADC info. There is also structure for IIO consumer HWC. Read row. There is an IIO consumer enable, IIO consumer disable, acquire the data. ADC probe. At that time they are allocating a consumer. Okay. And disable. This is I think a bit extended details of implementing or connecting two different IIOs. Okay, we got somewhat idea. If we go to our notes, let's see how many answers we got. Okay, we got to know about IIO's subsystem. Yes, we got to know. There is some very well explained details on the documentation. How does SPI2C communication layer works? That they explain, but did not we get yet. We need to. We'll look at driver. Look at some driver. Driver. Understand this. Yes, user space. We got to know about the files which is populated to user space files. Populated. SFS and yeah. Right. Okay, we have some information now. We can now go to the drivers. We will walk through the driver in the next video. Thanks.